Hello, everybody. Thanks so much for the positive feedback and encouragement so far. In this video, I wanted to answer some users' questions to continue that dialogue. So the first question that I'll take is user RPD3TD3HX asked some questions related to how copulas can be applied. The first question is, how can you fit data to a copula? Shouldn't you go the other way around? So let's clarify what we mean by fitting data to a copula. In the context of this question, you can think of a copula as a black box which learns the statistics of the data that you feed it. This is the fitting data to the copula part. The sampling part is, once you learn the statistics, generate some synthetic data that looks like the original data. So to fit a data set to a copula, you need to determine which copula you want to use. If you have some underlying information about the data generation process, which gives you an idea of what sort of copula may be appropriate, that may be one way to determine this. For example, if you know that your data generation process has tail dependence, for example, then you could choose a copula that has the ability to model tail dependence. If you don't know anything about the data generation process, you may want to choose one that gives you the best fit, and there are algorithms that can determine which copula may be the best fit. So that's step one in terms of fitting data to a copula. Step two is then to say, okay, if I have a parametric form of a copula, what is the parameters or parameter set? What values of parameters best fit the data that I'm trying to model? So this can be done using maximum likelihood estimation or inversion based on Kendall's tau. This was covered in a different lecture, but for the purpose of this question, I just to reiterate, maybe the phrasing is confusing here, but fitting data to copula is really what it means is given a data set, I want to build a model from that data set. And that's all the fitting the data means, is you're fitting your data to a copula model. The second part of this question was, how can you sample from the copula? So once you fit a model to the data, you can generate data from that model. And the whole reason to fit the model to the data is so that when you generate data, the statistics of that data model or mimic the underlying data that was used to fit the model. So this is a process of sampling from, this is what I mean by sampling from the copula. Conceptually, it's really the same as sampling from any sort of distribution. There's just some technical details of how to get there with copulas that may be different than sampling from a normal distribution, for example. But conceptually, it's the same thing. I hope that helps clarify this question. The next question is user XF5PK80W6G asks, in figure 1 in lesson 7, aren't all the inputs for copulas between 0 and 1? And if that's the case, how come the scale in this figure is varying, for example, in this case, between -2 and 1, and so on? These values do not seem like they are between 0 and 1. And so this is a great question. And so to go back to the premise, the input and output of a copula is always between 0 and 1. So this is a correct understanding. You can remember this by remembering that the output is always between 0 and 1 because the copula is a cumulative distribution function, which the property of a cumulative distribution function is that it is always bounded between 0 and 1. And the input is always between 0 and 1 because this is a fundamental property of the copula function. And you can also remember this by recalling that the marginal inputs to the inputs to the copula are also distribution functions. So everything is between 0 and 1. So that didn't help answer this question. So let's now get to this question. I think this question arises from perhaps a confusion as to what this figure is representing. So figure 1 in lecture 7, this figure right here, is showing something different. What it's showing is different marginal distributions. In this case, two normal distributions. In this case, a beta and a Cauchy. In this case, two exponential distributions the marginal distributions have been coupled together with a Gaussian copula with a rho parameter of 0.8. So the copula function is a function that combines marginal distributions together. And the copula function adds some dependence. Whereas if you didn't add any dependence, those two marginal distributions would be independent of each other, but real world data often has some dependent structure associated with it. And so what the copula is doing is it's combining these marginal distributions into a joint distribution. Now, because marginal distributions can take on any range of values, that's why you see a range of values in these plots here. These plots are not samples from the copula itself. These plots show samples from the joint distribution, which was generated using this copula. I hope that helps. Okay, so question 3 is, user CP3OD8JW2J asks, what is the reason for not obtaining the exact value of the parameters when fitting copulas through Kendall's tau? So this is a tricky and good question. So what I'm showing here is that there exists a theoretical relationship between Kendall's tau and the copula. That's shown with this first formula here. This is actually, in fact, this integral equation is how the relationships between Kendall's tau and copula parameters are derived. You can plug in a closed form for a specific copula and then do the necessary mathematical manipulations to solve for the copula parameter. So there is no loss in accuracy in this theoretical relationship between Kendall's tau and the copula parameter. However, when you are estimating this with a limited amount of data, you don't have the true value of Kendall's tau. You actually have an estimate of Kendall's tau, which can be represented with a hat symbol, typically in statistics. So this estimate, in turn, leads to an estimate of the copula parameter, which has some deviation from the true underlying parameter, which is the true underlying parameter is likely unknown. So the same issue actually exists with maximum likelihood estimation as well. It's just that you have some different properties depending on which estimator you choose to use. Maximum likelihood, for example, gives you some nice statistical properties such as statistical efficiency, while Kendall's tau is nice because it's just simple. It's simple to compute. So depending on what you need for your specific application, you would choose the specific estimation procedure. But that kind of gives you a background of the relationship between Kendall's tau and the copula parameter and the exactness of that. And the final question that I'll take today is user Antoine Guy 9536 asks, in reference to the Vine copula in lecture 9, he asks, why do we use residuals and why did we use profit model data rather than real data? So why did we use residuals? This is actually a common practice when modeling time series data in statistics. So let's go back to try to understand what we're trying to do here. Like, we're trying to capture the dependent structure between the returns of the various tokens that we're modeling. And so there are many ways to do that. In this example, what's happening is that the profit model, if we look at how it's used, the profit model is trained on a specific token. It's trained on the return data of a specific token, and then it predicts future returns for that specific token, right? And so what it's doing it for each token independently. So it's doing it for Bitcoin, Ethereum, and Filecoin independently. And now what we're saying with this Vine copula model is we're saying, okay, what we know to be true, or what the assumption of this model is that in fact they are not independent. In fact, there is some dependence between them. And that's what this Vine copula is modeling. And so to capture that dependence, what we do is we look at the residuals of the forecasts and then we basically model the joint distribution of those residuals. So why residuals? This is the direct answer is this is one way to capture that dependence between the returns of the different tokens that we chose to model. There are other ways to model that dependence, but the residuals is a way that's used, and it's popular in time series because of certain properties that it provides. So this leads to the second question, actually. Why do we use profit forecasts for the modeling, and why don't we use the data directly? And the answer here is that this is really kind of the basis of the example. If we didn't use profit to make a forecast, then there is no concept of a residual. And in that case, you're going to be modeling the returns of the returns of each token directly, rather than through a residual. That's another way to do things. It's just in this example, we chose to do it in this way. I hope that helps, and I know that there are more questions, and I'll try to address those in a future video. Thanks again for watching.